Now, when we explore a different kind of wave now with sound, sound is a particular kind of wave, and we're going to spend this unit talking about sound. So if you imagine this right here being a tuning fork and the arm of the tuning fork going back and forth, and then these dots representing the air molecules, this tuning fork is going back and forth. And if you notice, these waves are going by, right? Now, what I want you to do is concentrate on one of these dots and see what happens here. So what happens with most folks is you think the dots are moving, across the screen, but it's actually the waves, right? The dots are just moving back and forth, back, forth, back, forth, back, forth, right? Now, these areas where the waves are like this, where they're all compressed together, those are compressions. And the areas where they're spread out like here and then here, are rarefactions. That's where the air is really spread out. And so the compressions we call as crests, the rarefactions are troughs. And these are longitudinal waves because the wave is moving this way, right? So the velocity, the speed of it's moving this way, and then the medium is moving back and forth. The medium is moving parallel to the speed of the waves there. And so as it moves across, and as these waves go from left to right, the medium just moves back and forth. So sound is a longitudinal wave. Now, in the terms of production of sound waves, every sound wave begins with a vibrating object. So waves in general are created with vibrating objects, right? So the vibrating tuning fork going back and forth, producing the sound waves. Again, the compression is the region where the density and pressure are at a maximum. That's where the molecules are all compressed together. And then a rarefaction is where the density and pressure are minimum. That's where the air molecules are more spread out. Sound waves again are longitudinal, produced by the vibrating object. And if we make the equivalence, right, so the areas where the waves are real, the molecules are real compressed, those are crests. And again, where the air is more spread out, those are troughs. And then where the air is normal, it's a node, it's where the air is normal. So as the waves move across, that medium is going back and forth. And that medium may be part of a crest or trough or node or in between at any given moment. Again, they're caused by vibrations. And sound waves go out spherically, and so that's important too. They spread out spherically as they go, and so as they spread out, you can imagine, if you're speaking and you're looking across the room, and you imagine your sound going out from your mouth, it goes out forward from you, but it also goes out and ahead of you, up above, or behind you. So it actually spreads out spherically. And then that sound decreases in intensity as we get further and further out. So this is how we could visualize it there. If we had a sound source here, we had a speaker, and the speaker is producing the sound and it's spreading out spherically. If we take a cross-sectional look at it, we can do that. And so we have, the wave front. So the front itself, if this is a crest here, right, is going out spherically. And this is like, taking an orange and slicing it in half, or looking at the cross section of it. There are rays, right, where they're direct lines. If you're talking to someone, there's a ray that's from you to that person. But it's not limited to that, right? If I'm talking to someone in the room, someone else in the room, on the other side of the room can hear me as well, because that sound is traveling out spherically to them as well. And so, again, they go out in 3 dimensions. In this case, we're drawing it, in a 2-dimensional way. And the circles represents the compressions, and then the rarefactions would be in between. Now, once that sphere gets really big, right? So imagine you're speaking and you're talking to someone on the other side of the room. That sphere is going to be pretty large by the time it reaches them. So those wave fronts are basically going to be coming towards them in parallel lines. And so, at these great distances, these fronts are essentially parallel planes, parallel waves. And we can call them plane waves. They hit the source, and sequentially there. and we can treat them as one-dimensional waves as they reach there. So essentially, they're still curvy a little bit, but by the time that sphere gets huge, they're pretty much almost straight lines. Now on the moon, if you imagine, you're on the moon and you're trying to talk to an astronaut on the moon, if you're on Earth, right, and you're yelling, you'd probably be able to hear the other person. But on the moon, with no atmosphere, there's no medium for the sound to go through. So you have to have a medium. And so on the moon, they're talking through their radio. And then inside their helmet, there's a speaker that's pushing the air back and forth, and so they can hear each other. And so you have to have a medium, right? You have to have a medium for sound. And the medium will determine how fast the sound will go through the air or the material or whatever it is. And so in general, it's the slowest in gases, and then faster in liquids, and then fastest in solids. And then speed also depends somewhat on the temperature, especially for gases. And so, I asked the question, why do you think, it's faster in solids than in liquids or in the gases? And most people talk about density, and that's essentially what's happening, right? You have the molecules that can propagate this wave more easily or more quickly because the molecules are close together. And so if you look at this, right, you have these solids here where the speed in meters per second is much greater. But then in liquids here, it's faster than in air. Now, if you noticed, in air at 0 degrees versus air at normal room temperature, maybe 15, 20 degrees, it's 343, it's higher. The reason it's faster in warmer air is because those molecules are already moving, and if they're already moving, it's easier for that wave to go through, and it goes through faster. The speed of sound can be calculated this way. We take 331 and we add that to 0.6 times the temperature in Celsius, and that will give us the approximate speed of sound in air. So for instance, if it's 17 degrees, we multiply 17 by 0.6, it's going to be about 341.2 meters per second. That's going to be how fast sound travels. And if you think about that, the height of the stadium itself is about 11 meters, right? So 11 meters, if you had 33, maybe 32 or so stadium heights in 1 second, that's essentially how fast the sound will go. Now, in terms of what we can hear, the audible range is about 20 hertz to 20,000 hertz. And the upper range decreases with age. That's because the sensitive hairs that are inside your inner ear start to break away, and the ones that start to break away and never grow back are the ones in the upper range. And so ultrasound is above 20,000 hertz. An example of that is a camera sending out sound that we can't even hear. It hits their subject, bounces back, the camera receives that, and they can know how far the subject is. We have ultrasounds as well for body imaging as well. Infrasound or infrasonic, we're usually, ultrasonic, infrasonic, those are the ones that we're more used to. The ultrasonic, and then infrasonic is below 20 hertz. And so with that, you have different examples of that too. Bats use ultrasonic, right? They actually, the sound bounces off the walls, bounces off their prey, and very rapidly, and they can get a picture of what's happening. Infrasonic, even in whale sounds, whale songs are below 20 hertz, and so the whales can hear that and perceive that in underwater, but whereas we can't. So when we hear sound, we can hear a higher or low sound depending on the frequency or wavelength. And so short wavelengths have high pitch, long wavelengths have low pitch. And in terms of frequency, high pitch means high frequency as well. And then low pitch, low frequency. But the wavelength, right? The wavelength's actually longer. So low frequency, long wavelength, high wavelength, and then short wavelength means high frequency. So they're inversely related to each other.